There are two standard orbital design problems that have to do with the perturbing effects of the Earth oblateness, or J2 term. One of them deals with nodal regression, and the other one deals with apsidal rotation. So let's start with nodal regression. We have now shown several times in several different ways that we can write the longitude of the ascending node of an orbit is equal to some initial value plus the secular rate of change of the longitude of the ascending node times however much time has passed since this initial value was measured. And this lambda dot sec term is given by -3/2 times the mean motion of the orbit times the central body radius squared over the semi-parameter of the orbit squared times the central body's J2 term times cosine of the orbital inclination. We can use this expression to find a set of orbital elements such that this rate of change, omega dot secular, is equal to the change in the motion of the sun. Remember, the sun completes a full circuit about the Earth in the same time that the Earth completes a full circuit about the sun. And so the perceptual motion of the sun in our sky, or at least of the mean sun in our sky, is given by 2 pi radians over the length of the tropical year, which is the length of time that it takes for the mean sun to fully return to where it starts. So we set this equal to -3/2 times the square root of mu over a cubed, which is the mean motion, times the Earth equatorial radius squared over a squared 1 minus c squared quantity squared, which is the semi-parameter squared, times the Earth's J2 times the cosine of the orbital inclination. And you can dial in combinations of semi-major axis eccentricity and inclination such that you get exactly this value. And so what does that mean? This kind of orbit is called sun synchronous, because your spacecraft in this orbit will always have the exact same orientation with respect to the sun. That means that the satellite will pass over the same points on the ground at the same mean local solar time. The advantages of this are that you will always get the same illumination conditions. So if you want to image the same bit of ground with the same illumination conditions, then you need something that is continuously changing its longitude of the ascending node, because the sun is going to be constantly moving throughout the year and changing your local illumination conditions for all other orbital types. Alternatively, you can create an orbit that exactly rides the terminator. The terminator is the line between the day and night side of the planet. And this is known as a dawn-dusk orbit. That means that your spacecraft on this type of sun synchronous orbit will always be exposed to the mean sun, which means that on average, it will always have its solar panels illuminated, which can be very advantageous if you don't want to carry large batteries to take care of eclipses. Now, you have to be very careful here, and this is a mistake that is often made. Remember that this is all an analysis, first of all, for only a first order treatment of only the effects of J2, but also this is matching to the rate of change of the mean sun. So this doesn't mean that you're always going to actually be exposed to the apparent sun. These orbits, the low Earth dawn-dusk orbits, still have eclipses, but their eclipse seasons are much, much smaller and much shorter in duration than those of other types of orbits. If you start working out the numbers, you'll find that for low Earth orbits, for things below 1,000 kilometers, and for small or zero eccentricities, this basically drives you to near polar orbits, so inclinations of close to 90 degrees. You can absolutely find other combinations of parameters where the inclination is not close to 90 degrees, but this will drive you to much larger orbits. And there do, in fact, exist very large sun synchronous orbits that don't suffer from eclipses, but all low Earth orbits. So all of the orbits where we tend to want to place imaging spacecraft and anything with instrumentation that is directly observing the ground, those all tend to be near polar orbits with moderates and major axes, and they do suffer from eclipses. So the sun synchronous orbit is an example of an orbit that is generated only due to the presence of this perturbation. It is taking advantage of the naturally occurring perturbation due to the Earth oblateness effect. However, there's other examples where you're trying to design an orbit whose characteristics are actually going to be destroyed by the J2 perturbation. And so you have to factor that into your orbital design. And the classical example of this is something known as the Molniya orbit. The Molniya orbits are named after a class of Soviet spacecraft that first utilized these. And the intent of these orbits was to provide coverage for as big a swath of the Asian continent and the bits of Eastern Europe that were encompassed by the Soviet Union as possible. So the United States at this time was just launching geosynchronous satellites, satellites that have an exactly 24-hour orbital period and just sit on top of a single point. And because of the physical extent of the continental United States, the geosatellites provided perfect coverage. However, Asia is wider than the United States, and the Soviet Union took up a lot more land area, and a geostationary satellite would not provide as good coverage for the Soviet Union as it would for the United States. At the same time, geostationary satellites really only work as geosynchronous platforms in near equatorial orbits, and the Soviet Union is also significantly further north than the continental United States. So both of these things made geosats a bad option. Instead, what the Molniya spacecraft did was to use very, very large eccentric orbits with their apogee directly above the Soviet Union. And so we're talking about eccentricities of around 0.4 to 0.7. And so these things would spend the vast majority of their orbit at apogee. However, remember apsidal rotation. The effect of the Earth oblateness is such that your argument of periapsis will continuously linearly change as a function of 2 minus 5 halves sine squared of the inclination. And so if you place a Molniya orbit at some arbitrary inclination, your argument of periapsis will be continuously moving, which destroys the whole point of the orbit. So what can you do to combat this? Well, we can solve for a critical inclination such that this term goes to 0. If this equals 0, then we get an inclination that is the arcsine of root 4/5, which is approximately 63.43 degrees. So you can set up your large eccentric orbit at this inclination, and it will produce a net 0 secular change in the argument of periapsis. And you should also note that this applies regardless of what body you're in orbit around. This is completely independent of what the equatorial radius is and what the J2 term happens to be. And so this critical inclination is the same for all major bodies. So for any planet in the solar system, you can set up a Molniya orbit at exactly this inclination. This does introduce a secondary problem in that there will be a nodal regression, but you can fix that by adjusting your period. And so by fiddling with the various knobs that you have to turn, which are basically the semi-major axis and the eccentricity of the orbit, then you can get to exactly the effect that you want. And so what these orbits look like is this. This is a 12-hour Molniya designed such that its apogee is directly over the Soviet Union. These dots are equally spaced in time, and so you see that it's spending the vast majority of its time above Asia. And then on the flip side, the other 12 hours is spending the vast majority of its time over the United States. And it's very, very quickly traversing perigee, which is basically over ocean. So in order to provide continuous coverage, you would need several of these spacecraft, but they provide much, much better coverage for this much, much wider swath of land because they are higher than GEO than a single equivalent geostationary satellite, which would be providing coverage at much lower latitudes. These are the two classical design problems associated with these effects, but of course, there's many others. And because J2 is such a dominant term, you can actually get a lot of predictive power by only considering these relatively simple expressions. At the end of the day, if you want to know exactly what is going on with your orbit, you need to treat the rest of the geopotential. But of course, there's also lots of other perturbing effects that you would also have to treat if you're trying to exactly track or exactly forecast what is going to be happening with your spacecraft. And some of these effects depend on time-varying quantities. And that makes the whole problem quite hard. Forecasting where a spacecraft is going to be is incredibly difficult. And a lot of the time, we don't even bother. We just track the spacecraft and measure its position, either using ground based observations or the GPS constellation if the spacecraft is equipped with a GPS antenna. All that said, it is entirely possible to incorporate the effects of the full geopotential, or as much of the expansion as you wish, in numerical integrations of your orbit. And all that's required is just a lot of bookkeeping.